Have you ever wondered how your computer does, well, anything so fast? We're about to pull back the curtain on one of the most basic, most fundamental things your computer does thousands of times a day: searching. Let's dig into how a machine finds exactly what it's looking for in, literally, the blink of an eye.
You know, every single time you search for a file or a contact in your phone or even just one word in a huge document, you're basically asking your computer to find a needle in a digital haystack. So how on earth does it pull off that magic trick so incredibly quickly?
All right, to really get our heads around this, let's use a simple analogy. Picture a giant, old-school phone book. I mean a massive one. This book, that's our data. It's a huge, ordered list, and our one job is to find a single specific name inside it. This is the core challenge of any search.
Okay, so if I handed you this phone book, what's the first thing you'd do? Your first instinct would probably be what we call the brute force method. It's simple, it's totally straightforward, and in the programming world, it's known as a linear search.
So how does it actually work? Well, it's exactly what it sounds like. You open to the very first page, look at the first name, Aronson, maybe, and you ask, is this it? Nope. Okay, check the next one, and the next one, and you get the idea. You just keep flipping the pages one by one by one.
Now, the good news is, you are guaranteed to find the name eventually. It will always work. But the bad news? What if the name you're looking for is Zimmerman? You might be there all day, checking every single entry until you finally get to the very, very end of the book. It's reliable, for sure, but man, is it inefficient.
But what if there was a better way? You know, a genius shortcut that lets you work smarter, not harder. This is where computer science really starts to feel like magic. It's called the binary search, and honestly, it's a complete game changer. So what is a binary search? It's a lightning-fast algorithm that's built on a really simple but brilliant idea: divide and conquer. Instead of checking every single item one by one, you strategically eliminate massive chunks of data with every single step.
So how does this work in practice? Okay, forget starting at page 1. You grab that phone book and you rip it open right to the exact middle. Let's say you land in the M's. If you're looking for Smith, you instantly know it has to be in the second half of the book, right? You can literally throw away the entire first half, from A all the way to M. Then, you just do the exact same thing on the much smaller section that's left.
And this is where the sheer power of this method just becomes mind-blowing. With a linear search, finding a name in a book with 1 million entries could take you up to 1 million checks. But with a binary search, the absolute maximum number of checks you would ever need is just 20. Think about that for a second. From 1 million possibilities down to 1 in only 20 steps. That's just an astonishing level of efficiency.
Okay, I know what you're thinking. That sounds way too good to be true, right? A genius shortcut that can search millions of items in an instant? Well, you're not wrong. There is one very, very important catch. A single rule that has to be followed for any of this magic to work.
Let's go back to our phone book. What happens if instead of a nice, neat book, I just hand you a giant, jumbled pile of pages with names in no particular order at all? Could you open to the middle and make any kind of useful decision? Of course not. The whole divide and conquer strategy just completely falls apart.
And that right there is the crucial prerequisite. For a binary search to work, your data, whether it's a list of names or numbers or files, it absolutely must be sorted. The entire strategy depends on that order to know which half of the data it can throw away. If the data is random, the shortcut is totally useless.
So this brings us right to the heart of problem solving in computer science. It's never really about finding the one best algorithm. It's all about choosing the right tool for the specific job you're trying to do. So how do we decide between our two methods?
Really, it all comes down to this one fundamental trade-off. On one side, you've got the simple brute force method that just plods through everything one by one. And on the other, you have this incredibly elegant divide and conquer method that just carves up the problem with every single step.
Let's just break it down. Linear search, yeah, it's slow, but it has 0 requirements. It'll work on any list, sorted or not, which makes it perfect for small lists or completely jumbled piles of data. Then you have binary search. Its speed is just off the charts, but it has that one huge requirement: the data has to be sorted. That makes it the ultimate choice for searching through massive, well-organized datasets, like a big company's entire customer database.
And that really is the key takeaway here.
You know, true efficiency in computing, and honestly, in problem solving in general, it isn't just about raw speed. It's about understanding the context, the trade-offs, and the rules of the game you're playing. Knowing when to use the simple tool versus the super powerful one, that is a skill all by itself.
Every single time your computer does something that feels instant, a decision just like this one is happening behind the scenes, a choice between different strategies. This is just one tiny example. So the next time you search for something and get that instant result, just remember the invisible rules and the clever trade-offs that are making it all possible. What other hidden algorithms do you think are shaping your digital world right now?